In 1998, two independent teams of astronomers pointed their telescopes at some of the most distant exploding stars in the universe, expecting to confirm something everyone already assumed to be true. Instead, they found something that terrified them. The universe wasn't just expanding, it was expanding faster every single day. And the deeper they looked, the more they realized this discovery wasn't just strange, it pointed toward a future for our universe and a hidden truth about its structure that most scientists never saw coming. Today, we're going to talk about that secret, one that's still unfolding, still being measured, and one that, once you understand it, changes the way you look at the night sky forever. Welcome back to the channel, where we take the universe's strangest, deepest secrets and explain them in plain, simple language in the spirit of Brian Greene, where cosmology becomes a story instead of a lecture. If you're new here, this is exactly the kind of thing we do every week, taking discoveries that quietly reshape our entire understanding of reality and breaking them down so anyone can follow along. Before we start, if you want more videos like this, hit subscribe. Stay until the end, because this secret gets darker the deeper we go, and by the end, you'll understand why some physicists genuinely find it disturbing. And if you're enjoying this, please hit like and share it with someone who'd find this fascinating. And let's get into it. For most of the 20th century, cosmologists debated one central question about the universe's future. Would it keep expanding forever? Or would gravity eventually pull everything back together in a big crunch? Either way, everyone agreed on one thing: gravity should be slowing the expansion down. Every galaxy pulls on every other galaxy, so the rate of expansion should be gradually decreasing over time, the same way a ball thrown into the air slows down as gravity pulls it back. In the 1990s, two teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, set out to measure exactly how much the expansion was slowing down, using a special type of exploding star called a Type Ia supernova as a standard candle to measure cosmic distances precisely. What they found instead, published in 1998, stunned the entire field. The expansion of the universe wasn't slowing down at all. It was speeding up. This discovery was so significant that it earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, and it forced physicists to accept the existence of something they still don't fully understand. To explain this acceleration, physicists had to introduce a mysterious component to the universe, one that pushes space apart rather than pulling things together. They called it dark energy. According to our best current measurements, dark energy makes up roughly 68% of everything in the universe. Ordinary matter, everything you've ever seen, touched, or measured, makes up less than 5%. The rest, about 27%, is another mystery called dark matter. Here's the unsettling part. Nobody actually knows what dark energy is. The leading candidate is something called the cosmological constant. Essentially, a fixed amount of energy built into the very fabric of empty space itself. The strange implication is that even a completely empty region of space with no matter in it at all still contains energy, and that energy pushes space apart. When physicists try to calculate this value using quantum field theory, they get an answer that's wrong by roughly 120 orders of magnitude, one of the largest, most embarrassing discrepancies between theory and observation in the history of physics. This mismatch is sometimes called the worst prediction in the history of physics, and it remains one of the biggest unsolved problems in all of science. Here's where the secret starts to get genuinely dark. Because space itself is expanding, and that expansion is accelerating, there are galaxies out there right now whose light will never reach us. Not because they're too far away today, but because the space between us and them is stretching faster than light can cross it. This creates something called the cosmological event horizon, a boundary beyond which nothing, not even light, can ever reach us again, no matter how long we wait. And it's not static. As the universe keeps accelerating, this horizon keeps shrinking inward, meaning more and more galaxies are crossing it every single day, permanently leaving our observable universe never to be seen or contacted again. We're not just failing to reach these galaxies. We are right now in the process of permanently losing access to most of the universe, one galaxy at a time. Right now, of the roughly 2 trillion galaxies estimated to exist in the observable universe, only a relatively small gravitationally bound cluster, our local group, containing the Milky Way, Andromeda, and a few dozen smaller galaxies will remain reachable in the very distant future. Every other galaxy over the coming tens of billions of years will eventually cross the cosmological horizon and vanish from view forever, redshifted into invisibility as the space between us and them stretches faster and faster. Physicists Lawrence Krauss and Robert Scherer published a paper making this point explicit. Far enough into the future, around 100 trillion years from now, any civilization looking up at the night sky will see almost nothing beyond its own galaxy. No other galaxies, no cosmic microwave background, no evidence the Big Bang ever happened at all. This leads to something that genuinely troubles cosmologists. We exist at an unusually privileged moment in cosmic history, one where the evidence for the Big Bang, the cosmic microwave background, and the large-scale structure of the universe are all still visible. Future civilizations arising trillions of years from now in an isolated galaxy with no visible neighbors might have almost no way of discovering how the universe actually began. Their night sky would offer no clues. Their physics might conclude, quite reasonably, that their galaxy simply always existed alone, floating in an otherwise empty void. In a very real sense, the universe appears to be erasing the evidence of its own origin, one galaxy at a time, and we happen to be looking at the sky during the narrow window where that evidence is still visible. You might wonder how astronomers can be confident about any of this. The key tool is redshift. As galaxies move away from us, the light they emit stretches to longer, redder wavelengths, the same way an ambulance siren drops in pitch as it drives away from you. By carefully measuring the redshift of thousands of galaxies at different distances, astronomers built out what's called the Hubble diagram, mapping how fast the universe is expanding at different points in cosmic history. Combined with the Type Ia supernova data from the 1998 discovery, and later confirmed by independent measurements of the cosmic microwave background from missions like WMAP and Planck, the case for accelerating expansion has become one of the most well-supported conclusions in modern cosmology. This isn't speculation, it's one of the most rigorously tested results in physics. What remains unknown isn't whether this is happening, but why. Or could dark energy be wrong? Maybe it's something else entirely? Some physicists propose alternatives like modifications to general relativity itself, rather than an actual energy filling space. But so far, dark energy remains the simplest explanation that matches the data. Does this mean the Milky Way will eventually be alone in the universe? Not entirely alone. Our local group, including Andromeda, is gravitationally bound tightly enough to eventually merge into one large galaxy, which will remain together even as everything else disappears from view. Is this happening quickly enough for us to notice in our lifetime? No, this process unfolds over billions of years. Nothing about the night sky will visibly change in any human lifetime or even across all of recorded history. If dark energy keeps behaving the way it currently does, the most widely accepted long-term future for the universe is something called the Big Freeze, or heat death. As galaxies drift apart and stars burn through their fuel, star formation will gradually slow and eventually stop entirely. Astronomers estimate the last stars will burn out somewhere around 10 to 100 trillion years from now. After that, the universe enters an unimaginably long dark era dominated by black holes, which themselves will eventually evaporate through a slow quantum process called Hawking radiation over timescales of up to 10 to the power of 100 years. What's left in the almost incomprehensibly distant future is a cold, dark, nearly empty universe expanded to such an enormous size that the distance between any two remaining particles is essentially infinite. Entropy will have reached its maximum possible value. No stars, no structure, no meaningful change of any kind, just a permanent, silent equilibrium. This isn't science fiction. It's the leading prediction based on our best current understanding of physics, and it follows directly from the same dark energy measurements we covered in Part 1. There's a second, more dramatic possibility depending on exactly how dark energy behaves over time. If dark energy strength increases as the universe expands, a property physicists describe using something called the equation of state parameter, or W, the expansion wouldn't just continue accelerating gradually. It could reach a point where it starts tearing apart galaxies, then solar systems, then planets, and finally atoms themselves, in a scenario physicists call the Big Rip. In this scenario, expansion becomes so violent that even the electromagnetic forces holding atoms together can no longer resist it. Physicist Robert Caldwell, who first proposed this idea in 2003, calculated that under certain models, this could theoretically happen in a finite, calculable amount of time, potentially tens of billions of years from now, rather than the near eternity required for a big freeze. Current measurements slightly favor the slower Big Freeze scenario over the Big Rip, but our precision on dark energy's exact behavior still isn't good enough to rule the Big Rip out completely. We genuinely don't yet know which of these two endings, a slow fade or a violent unraveling, actually awaits the universe. Now we arrive at the possibility that many physicists find the most unsettling of all: vacuum decay, sometimes called false vacuum decay. Here's the idea. According to the standard model of particle physics, the Higgs field, the field responsible for giving particles their mass, currently sits in a state that appears stable, but calculations suggest it might actually be sitting in a false vacuum, a low energy state that only looks stable, like a ball resting in a shallow dip on a hillside, unaware that a much deeper valley exists just beyond the next ridge. If this is correct, it means the universe's vacuum isn't in its true lowest energy state. And in quantum mechanics, systems can occasionally tunnel through energy barriers they classically shouldn't be able to cross. If a small region of space somewhere in the universe tunneled into that lower true vacuum state, it would create a bubble of genuinely different physics, different particle masses, different fundamental forces, different chemistry, incompatible with anything resembling atoms, stars, or life as we know it. That bubble wouldn't stay contained. It would expand outward at the speed of light in every direction, converting everything it touched into this new incompatible vacuum state, instantly and irreversibly. What makes vacuum decay uniquely unsettling isn't just the destruction, it's the complete absence of warning. Because the bubble expands at the speed of light, there would be no way to detect it coming. Light from the approaching destruction would arrive at exactly the same moment the destruction itself did. From our perspective, everything would simply be normal. And then, instantaneously and without any prior signal whatsoever, it wouldn't be. Physicist Joseph Lecken and colleagues at Fermilab published calculations in 2013 based on the measured mass of the Higgs boson discovered at the Large Hadron Collider the year before, suggesting our universe's vacuum may indeed sit in this precarious metastable state, though their own calculations also suggest that, statistically, this kind of decay is expected to take vastly longer than the current age of the universe to actually occur, making it exceedingly unlikely to happen anytime soon. Still, the fact that this remains a live, seriously discussed possibility in mainstream physics, that the very fabric of empty space itself might not be as stable as it appears, is exactly the kind of secret that keeps some physicists up at night. Given everything we've just covered, it's worth pausing to add some perspective. The timescales involved in the Big Freeze span trillions upon trillions of years, utterly incomprehensible compared to a single human lifetime or even the entire span of human civilization. The Big Rip, in its more extreme forms, would still take tens of billions of years at minimum, and vacuum decay, according to the best current calculations, is statistically expected to be an exceptionally rare event on cosmic timescales, and if it happened even once, somewhere far across the universe, we still wouldn't see it coming until the instant it arrived, making worry itself quite literally pointless. None of these scenarios pose any meaningful threat within any time frame that matters to us personally. What makes them worth understanding isn't fear, it's the sheer scale of what modern cosmology has revealed, a universe far stranger, far more fragile in principle, and far more temporary than anyone imagined just a few decades ago. Perhaps the deepest part of this entire story isn't about black holes or vacuum bubbles or disappearing galaxies. It's about what it reveals regarding the limits of human knowledge. We happen to exist during a uniquely fortunate sliver of cosmic time, when the evidence of the universe's origin is still visible in our sky, when galaxies are still close enough to observe, when the light from the Big Bang itself still reaches our telescopes. Every measurement we've made about dark energy, about the accelerating expansion, about the eventual fate of the universe, all of it was only possible because we happened to be looking at exactly the right moment in an almost inconceivably long cosmic timeline. Trillions of years from now, whatever intelligence might exist in whatever isolated pocket of the universe remains, may never be able to reconstruct any of what we've just described. In a strange way, this video itself, this exact explanation of the universe's darkest secret, might be one of the only records of it that will ever exist anywhere at any point in cosmic history. So, that's the darkest secret modern cosmology has uncovered. Not a monster hiding in the dark, but the dark itself, slowly and quietly consuming everything we can currently see, while something as ordinary as empty space may be hiding a fragility no one expected. If you found this fascinating, please hit like, share it with someone who'd enjoy thinking about this, and if you haven't already, subscribe to the channel so you don't miss what we cover next. Or let us know in the comments of everything we covered today, which possibility unsettles you the most, the big freeze, the big rip, or vacuum decay. I genuinely love to hear your thoughts. See you in the next video with a new question and a new mystery to explore. Take care.